All right, so it is a pleasure to have Chen Yiming from Princeton here to talk about spectral form factor in gauge theories and strings on the wormhole. Thank you.
Okay, I want to thank the organizer for giving me the opportunity to present my work here. And I will change the topic of the day slightly and talk about gauge theories in this talk. So this will be based on a paper that I wrote earlier this year, and as well as some unpublished results by myself. But I should acknowledge that Juan's discussion, and also I've talked to Steven Schenker about my work. Their comments are very useful for forming the ideas here. So my plan is to first give a brief review about the problems about black holes. I believe to this audience, people are very familiar with this topic, but I will try to highlight some less appreciated aspect of the problem. Then I'll talk about the spectral form factor in gauge theories. I will start with the free theory, free large N gauge theory. And then I'll talk a little bit about what will happen as one turns on the Hooft coupling. Okay, so a quantity that has raised a lot of attention in recent years is the so-called spectral form factor. And usually it is defined as the square of the analytically continued partition function. So Z of beta plus IT. Let me try to use this. So you define it by squaring the analytically continued partition function. So in this talk, I will be focusing on theories that have definite Hamiltonian. So there is really no distinction of the quantity itself and the square of the quantity. And there have been some often discussed universal feature of this quantity. So here, I believe this is a plot that you've all saw before. That is the spectral form factor for the SYK model. So for a general chaotic quantum system, at a short time, the spectral form factor decays. So that is called the slope in this diagram. And the decay is governed simply by the continuous density of state. But the spectral form factor doesn't decay forever. At some point, it starts to turn over and it starts to increase linearly, at least in the chaotic quantum systems. And the linear increase in the spectral form factor is governed by the random matrix statistics in the underlying spectrum. And the discreteness of the spectrum is usually associated to the late time behavior of the spectral form factor, which asymptotes to a constant value that is called a plateau. So now, another reason that the spectral form factor is an interesting quantity to look at is because it's a natural quantity to compute in gravity. So semi-classically, if we want to compute Z of beta plus IT, we simply fix the boundary length of the space-time to be some complex number beta plus IT, and look for the bulk solution that fills in this boundary. So if we consider this for a black hole, semi-classically, it's just given by a complex black hole space-time. That is just an analytic continuation of the usual black hole solution. So it is a very natural extension to the usual Gibbons-Hawking type thermodynamics story. Now, there is a digression that I want to make here. So rather than considering the canonic example spectral form factor that people usually discuss, sometimes it's actually better to consider a different version of the spectral form factor, which I call a microcanonical example version. So instead of summing all the energy eigenstates with a Boltzmann factor, here I'm summing over all the phases with a Gaussian window centered around some particular energy E and with some width delta, okay? And I will follow the convention in the literature and denote this quantity by Y here. So why do we even bother considering this more complicated quantity? There are actually a few good reasons to consider the microcanonical example one rather than the canonical example one. So the first reason is a generic feature in higher dimensional theories that if we consider ADS Schwarzschild black hole, the simplest kind of black hole, and consider the quantity Z of beta plus IT, there is actually a Hawking-Page transition in this quantity as you increase T. And the thermal ADS saddle actually dominates over the black hole saddle at some very short time, at a time that is of order beta. So the way that you see it is the following. So let me remind you that in higher dimensional ADS, on the real axis of the beta axis, or as you change the temperature, in the low temperature phase, or when beta is relatively large, the bulk is dominated by a thermal ADS saddle, which I draw here as a cylinder, where the time is periodically identified. But as you go above the Hawking-Page temperature, in the high temperature phase, the bulk is dominated by a black hole saddle point. Now, as we want to, when we want to consider this Z of beta plus IT quantity, we are simply asking what are the phases in the complex plane of beta. Then the idea is that this phase transition point on the real axis of beta actually gets extended into a one-dimensional line in the two-dimensional complex beta plane. And you see that if you do this exercise, you actually see that this line bends leftwards or bends towards the side of the black hole. So if you start at some place, for example, here, you start in the black hole phase and you increase the imaginary part in beta plus IT, so you go up there. At some t that is relatively short, you actually transit into the thermal ADS phase. This is also saying that if you really care about the spectrum of the high energy states corresponding to the black hole, it's better to consider the microcanonical example rather than the canonical example. Okay, so there is actually another benefit of considering this Y quantity rather than the Z quantity, is that this Y quantity decays relatively fast at short time. So it makes it much easier to expose other possible contributions to the spectral form factor. So how do we see that it decays very fast? So as a toy example here, we could consider a case where the density of state is almost flat. So here I'm replacing the discrete sum in the spectral form factor, the sum over energy eigenvalues, eigenstates, into a continuous integral, and I plug in the density of state here. So if we consider a toy example where the density of state is flat, then the formula here is simply a Fourier transform of a Gaussian function. So we know that the final answer must decay also as a, it also has a Gaussian decay as a function of t squared. So we see that in this toy example, the function actually behaves like e to the 2s at some energy E minus delta squared times t squared. Now, if we consider an ADS black hole, usually it's usual to choose the energy window delta to scale as 1 over square root of G Newton, so that both terms is on the exponent would have the same 1 over G Newton scaling. In other words, we can ask, when does this quantity decays to exponentially small? And we see that it actually decays to exponentially small at order 1 time. Okay, so in this graph, I'm plotting the logarithm of the spectral form factor. And the place where this curve crosses 0 is the place where the quantity decays to exponentially small. And I want to highlight here, it happens at a very, very short time. It happens at order 1 time.
Sorry, Yiming.
Yes.
If delta is of order 1 over square root of G, isn't that just the same as you would have had in the thermal ensemble?
Exactly, but the thing is, the answer at t equals 0 will be basically the same, but the canonical and microcanonical example do not have to agree when you go to later time.
But it's not coming because you made the width smaller than the thermal ensemble. It's just because you have a step function, a Gauss somehow.
Yeah, it's because of the Gaussian function. This is related to the fact that I told you earlier that there's a difference here. If you consider the canonical example, actually, as you increase t, you are actually looking at different energy windows. So here there is a transition into thermal ADS phase. So physically, you are looking at a low-lying energy states. But you could restrict yourself to the high energy states, and then it gives you a very fast decay.
Yeah, but you're not. It doesn't. I mean, is there a reason why you don't also take the energy window smaller? Would that make life more difficult? Or?
Yeah, you could take it smaller. The one thing here is that if you take the delta to be larger, as you see from this formula in this toy example, it decays faster. So it makes it easier to expose other contributions.
Yeah.
So if you make delta to be small, the initial decay will be slow, then you might not see other stuff that you are interested in.
Okay.
So it's just a trick. It's not something that really important physically. It's a trick to expose other contributions. Okay. So now I want to highlight that this is a challenge to discreteness at order 1 time. Why? Because the semi-classical answer that you get, for example, from the density of state of the black hole, decays to exponentially small at order 1 time. And this is very difficult. This will be very difficult to explain if we recall that y is actually a discrete sum. It's a discrete sum over exponentially many terms, and each term actually gives you an order 1 phase. So unless some miracle happens, and we don't expect that the generic spectrum of a black hole to have such a miracle property, we don't expect the answer to really decay to exponentially small. Now, of course, this is a well-known puzzle. For example, it was raised by Sashankar and Stanford. Here, I only want to highlight the property that this is already a puzzle at a very short time when you look at the correct quantities. So as Sashankar and Stanford pointed out, that at late time, generally, we will expect wormhole geometries to give us increasing contribution to the spectral form factor, which is called the ramp. But a question that is generally unclear is whether the ramp already kick in at this super early time that is of order 1, or is there something maybe in between the initial decay and the late time ramp? Okay. So very good. So in this talk, I would try to be very modest and try to just consider these questions in larger gauge theories. So the idea is that I would take the gauge field to be SUN and all the matter field in the adjoint representation. Now, this of course include theories with non-gravity dual. For example, we could consider the 4-dimensional Angstrom super Young Mills. Now, the idea is that we put the theory on a compact spatial manifold. So here I draw the time direction, which is a Euclidean circle. In principle, it has a complex length. The spatial manifold, we could consider if, for example, on S3. The crucial thing is that I want to put it in on a compact manifold so that the theory has a discrete spectrum. Okay. So in this talk, I will first try to understand the spectral form factor for free gauge theory. So that is a case that we should be able to solve exactly. Then we'll ask what happens when you turn on the interaction. So what's changed and what remains unchanged. It actually turns out that after you sit down and do this calculation, you see that even in the free theory, there's already an interesting puzzle that you need some interesting ingredients to solve. Now, okay, so now let me start to discuss the spectral form factor in free gauge theory. Now, before we really talk about the spectral form factor at large time, we should first try to understand what the standard thermodynamic phases of the theory are, or in other words, we should first understand what the spectral form factor is at t equals to 0. Similar to the Hawking-Page transition that I mentioned earlier, which is a phenomenon strong coupling, even when the coupling goes to 0, or in the free limit, there is also a Hagedorn phase transition. So this was pointed out, for example, in these papers. The idea is that if you look at the canonical example partition function, as you vary the temperature, in the low temperature phase, or in other words, when the temperature is lower than the so-called Hagedorn temperature, the free energy of the theory is of order 1. While when the temperature increases above the inverse the Hagedorn temperature, the free energy becomes of order n squared. Now, because of the particular scaling with n, in the free energy, this is also sometimes called the deconfinement transition. Namely, the low temperature phase is the so-called confined phase, while the high temperature phase is the deconfined phase. There are some necessary background knowledge that I need to review here. So such a phase transition in gauge theory can in general be diagnosed through an interesting observable that is called the thermal holonomy or the Polyakov loop. So what is the thermal holonomy? The thermal holonomy is simply defined as basically it is roughly speaking a Wilson loop that wraps around the Euclidean time circle. With a slight technical difference is that here we are integrating the zero mode of the time component of the gauge field, namely the gauge field smeared on S3, integrated over the time direction. Okay? So it's kind of a smeared version of a Wilson loop, and it's called the thermal holonomy. It's simply an n by n unitary matrix. And from this unitary matrix, you can construct a set of order parameters. So for example, the most famous one is probably the trace of this unitary matrix normalized by 1 over n. And this is the so-called Polyakov loop, more accurately, the Polyakov loop in the fundamental representation. And in principle, you could consider other order parameters, for example, trace u squared, trace u cubed, etc. These are order parameters in the sense that if these operators, they have non-zero classical VABs, this will signal the breaking of the Zn central symmetry or the subgroups of Zn central symmetry in the gauge theory. So this is a point if you've never seen this before, it would not be important in the following. So I don't want to go into detail of that. Okay. So alternatively, you can also look at simply look at the eigenvalues of the holonomy matrix. So it's a unitary matrix, so it has n eigenvalues which are pure phases, which are denoted by theta 1 to theta n. Okay, and in the large n limit, these phases they form a continuous density eigenvalue density rho of theta. Let's say from minus pi to pi. Now, the thermal partition function of a free gauge theory can simply be computed exactly by reducing the full path integral into a matrix integral of the thermal holonomy. In other words, the canonical partition function, canonical example partition function z of beta can be expressed as an integral over the thermal holonomy matrix with some particular action that won't be very important in the following. So that you don't really need to look at a specific form. But what are the inputs to this action? The inputs are a bunch of functions that I denote by little z here. And they are fully determined by the single particle spectrum on the spatial manifold. For example, if you consider pure SUN Yang-Mills theory on S3, there are just some simple function of beta that you can easily work out. And this is a fairly concrete matrix model. And by solving this matrix model, you can get the exact canonical partition function of the gauge theory. Now, as I mentioned earlier, in the canonical example, as you tune the temperature, there are two different phases, the confined phase and the deconfined phase. In the low temperature phase, in other words, the confined phase, if you look at the saddle point of the holonomy matrix, its eigenvalue is basically what I call the ungapped eigenvalue density. Namely, the eigenvalues of the holonomy matrix distribute uniformly between minus pi to pi, okay? And in this phase, if you, for example, compute the expectation value of the Polyakov loop, namely trace u, because it's uniform, you find that the expectation value is simply 0. Now, something changes as you go above the Hagedorn temperature. In the phase that is with temperature above the Hagedorn temperature, you find that the saddle point of the matrix actually has a gapped eigenvalue density distribution. Okay, so it opens up a window between, for example, minus pi and the starting point of this eigenvalue distribution. And now if you plug this specific distribution into the formula of the Polyakov loop, namely trace u, you see that it becomes non-zero. So in other words, the Polyakov loop here can be used as an order parameter to diagnose whether the theory is in the confined phase or deconfined phase.
Sorry, maybe I'm remembering this wrong, but I thought in the phase on the right, they should sort of all be on top of each other.
So as you raise the temperature higher and higher, the distance between these 2 points becomes smaller and smaller, and the eigenvalues start to be bumped up.
There's two competing saddle points, though, so I thought there was a sharp transition from uniform to very non-uniform.
Right. So, well, I think that's the. I don't understand what's the difference of what you're saying and what I said, because in the low temperature phase, the dominant saddle point is a completely uniform one.
Yeah, I agree with that.
Yes, and in the high temperature phase, the dominant saddle point is basically this gapped one.
Yeah.
But exactly like the exact distribution here would depend on the temperature. So as you raise the temperature even higher, the eigenvalues start to be closer and closer together. Okay.
Yeah, I'm probably just not remembering exactly.
Okay, yeah. So one last point here is that this hackathon temperature is determined very easily from the matrix model. In other words, it's simply a solution where the first little z function, the z1 function, equals to 1. So that is a little detail that I would need later. Okay, and this phenomenon that Polyakov loop has a valve in the high temperature phase can be also understood as pointed out by Edward Wheaton in his 1988 paper from a string wall sheet picture as strong coupling. So as I said earlier, in the low temperature phase given by a thermal ADS, and in the high temperature phase is given by the black hole. And the difference between the two is whether the Euclidean time circle is contractible or not. So as Edward pointed out in his paper, you can basically look at whether the Polyakov loop has a valve or not by considering a string wall sheet that wraps around the Euclidean time circle. So in the low temperature phase, since the Euclidean circle is not contractible, you cannot have a classical string wall sheet that just wraps on the Euclidean circle. So that tells you that at the classical level, the expectation value of the Polyakov loop is equal to 0. But in the high temperature phase, since the Euclidean time circle is now contractible at the horizon, it shrinks to 0 at the horizon, so you can just wrap a classical wall sheet on the geometry. And at the classical level, the expectation value of the Polyakov loop, or more accurately here, it should be a localized Wilson loop, will be given by the Polyakov action of the string on this background, and it is non-zero. Okay. And the idea is that the different eigenvalue distributions of the holonomy are the analog of different bulk geometries in the free theory. Now, there is just one last detail before I go on and discuss the spectral form factor. The last detail is that there is a difference between the canonic ensemble partition, canonic ensemble and the microcanonic ensemble. So here in the canonic ensemble, there is a first order transition at some particular temperature, the hackathon temperature. But a first order transition actually corresponds to a range of energy in the microcanonic ensemble. In other words, in the microcanonic ensemble, there is a different saddle point in between these two that I talked about. And that saddle point would be an ungapped saddle point, but it has a cosine theta fluctuation in the eigenvalue density of the holonomy. And now the idea is that we can start from either this saddle point or this saddle point and continue to large time in the spectral form factor, right? So the reason that I wanted to mention this phase is because since it is an ungapped eigenvalue density distribution, the formulas are actually much simpler in this case compared to this case. So you can first analyze what happens in this case and then try to extract some lessons. Okay, so now let's start to talk about the spectral form factor. The idea is that if you just use the saddle points that are already known in the literature, for example, this ungapped saddle point or this gapped saddle point, and you continue the Y quantity to real time, you see that it gives you an exponential decay, just similar to what I said about the black hole. And you see it decays to exponentially small also at some time that is of order 1. Again, this is puzzling because, as I said, the spectral form factor is a sum of exponentially many order 1 terms. And even in the free theory, there is no particular reason that we should expect that the spectral form factor gets so small. So this is a discreteness problem that you already see even in the free theory. Of course, here, we don't really expect the RAM to show up since there is no random matrix statistics in the free theory. On the other hand, the spectrum already has very large degeneracies. So it's very different from the spectrum that you expect of the black hole. But there must be something else that replaces the initial decay because the spectrum is discrete nonetheless. There is an easy remedy to the problem that I just said. If you already consider the pure Yang-Mills theory on S3, since in the free theory, all the energy eigenvalues are integers because the single particle spectrum on S3 are integers. Of course, here I set the radius of S3 to be 1, for example. Then the spectral form factor must be a periodic function since all the levels are spaced by integers. In other words, we have this initial decay, then at, for example, t equals to 2 pi, this initial decay must come in again and give you a rising behavior in the spectral form factor. But this is not a good enough solution to the discreteness problem because you could have two situations. In one situation, the combination of this early decay and its periodic recurrence simply prevents the answer to be exponentially small. But you could well have another situation where there's still a very large gap in between these two saddle points that the spectral form factor is exponentially small. So in the later case, you still need something else to prevent running into a problem with discreteness. Also, we could consider putting the theory on some arbitrary manifold, not S3. Then the single particle spectrum would not have this, does not have to be necessarily spaced by integers, and it won't be regular, so there will certainly be no periodicity. So this argument that this way out cannot be a general mechanism, okay? Now, I don't really have time to go into the detail, but what happens is that it turns out that we are actually missing many new saddle points. And these new saddle points can be found by studying the following matrix integral. So you consider this microcanonical example 1, which is some sort of inverse Laplace transformation of the canonical example partition function. And the canonical one is simply given by this matrix integral. So you are so when you solve this problem, you are finding the saddle point of beta, and at the same time, you are finding the saddle point for the holonomy matrix U. And as I mentioned briefly, this analysis that was done in my paper is simplest for the intermediate range of energy where the short time saddle is ungapped. So the answer from the matrix model is very simple in this case. Now, let me just briefly tell you the conclusion of the analysis. So in this range, namely the intermediate range of energy, the saddle point to this problem are fully characterized by the complex solutions of the following equations. So you have a set of equations which is Z1 equals to 1, Z2 equals to 1, etc. So on the complex plane, you have many solutions to this set of equations. For example, the solutions of Z1 equals to 1 are these points that I draw here. And in principle, you also have many solutions of Z2 equals to 1, etc. Okay? And the short time saddle that I mentioned earlier is a solution to the equation Z1 equals to 1, namely the point that I circled in red here. I mentioned that if the underlying spectrum is spaced by integers, there is a periodicity in the spectral form factor. In that case, we know that the solutions to this equation Z1 is to 1 also should appear periodically. So in other words, the solution also appear when you shift the value of beta in the imaginary direction for some amount. But the crucial new ingredient here is that there are many other solutions where they solve the equation with Zn equals to 1 with n greater or equal to 2. And these saddle points are very different from the saddle points that are known in the literature in the way that they don't really have, they do not have a cosine theta variation. On the other hand, they have cosine n theta variation in the eigenvalue density. So here I'm just, if you do not follow the detail, it doesn't matter here, I'm showing you a snapshot of what could happen, is that after the initial decay that was given by the cosine theta eigenvalue density, you actually find a new saddle point that has a cosine 2 theta fluctuation in the eigenvalue density that gives you a increasing and then decreasing contribution to the spectral form factor. And in general, depending on the detail of the theory, you could have many other saddle points as well. It's fully characterized by this kind of lattice that I drew here. Now, I mentioned that the reason that I stick to this intermediate range of the energy is simply because the formula is simpler. But once you understood that, you could also go to even higher energy, namely energies that are above the Hagedorn transition. The analysis is mathematically more complicated, but you see that the similar structure still remains. For example, the initial decay, as we know that it is given now by a gapped eigenvalue distribution. While what could save you from the spectral form factor becoming exponentially small is that there is a new saddle point, which corresponds to a multi-cut, in this case, a two-cut distribution in the holonomy, eigenvalue of the holonomy. Okay. So the conclusion is that these saddle points combined can prevent the spectral form factor from becoming exponentially small. In other words, we've solved the discreteness problem in the free theory. So there's another point that I want to comment on is that these saddle points, they are already very distinct in the sense that they can be distinguished by the order parameters that I mentioned earlier. Not just the expectation value of the Polyakov loop, but also the expectation value of trace U to the n in general. A better way to say this is to characterize them by the fact that they actually preserve different subgroups Z little n of the center symmetry in the gauge theory. So for example, here the initial decay will be a saddle point that breaks the Zn symmetry, Z capital N symmetry entirely, while this late time saddle point would actually preserve a Z2 subgroup of the Zn symmetry. Now, there is an analog, and perhaps it's a more interesting story for if you consider the spectral form factor for a gas of highly excited strings. So there, you actually also find a new family of saddle points, which are the generalizations of the Horowitz-Polchinski solution. So this story was also discussed in my paper, but I won't have time to go into that. Okay, so what's the lesson that we learned so far? So basically, we can ask, what do these saddles actually mean? Of course, they save us from running into a problem with discreteness, but we could say a little bit more about them. For each of these saddle points, we can just use the explicit solution to compute their contribution to the density of state. And we actually see that the saddle points with n greater than 1, they have a physical meaning that they correspond to tiny ripples in the density of state. In other words, here I'm drawing schematically of all the energy eigenvalues of a free theory, let's say on S3, so that they are all spaced by integers. Now there is overall coarse-grained density of state, which I draw by this blue curve here, and that gives us the initial decay. But in general, since the spectrum is discrete, you expect corrections to that. And in this free theory case, you actually find that there are these ripples in the density of state, which I draw by the red line and the green line here. And they actually give you the rising behavior in the spectral form factor. Now, the matrix model that I showed you earlier is smart enough to produce these saddle points, of course, as it should, which are necessary for consistency with the underlying discreteness. These saddle points, they are exponentially suppressed compared to the short time saddle point. But I want to emphasize that they still give you a very, very large answer in the spectral form factor. In other words, their contributions are still of order e to the n square. So they are not very small contribution. So far, the story seems to be very far from gravity, but I should emphasize that even at this level, one can already relate this story to gravity. One can compare similar new saddle points to gravity solutions in a slightly different context, namely the supersymmetric index for BPS states. So this was discussed in this recent nice paper. So in the context of BPS states, you are not considering the energies anymore, but you could consider a spectral form factor for the charges of the BPS states. The idea is that the usual supersymmetric black hole will also give you an answer that decays forever. So here, the decay doesn't start at tau equals to 0, which is because of some technical reason. But basically, this curve will correspond to the supersymmetric black hole. And for later so-called time, you will also run into a discreteness puzzle. Now, in this case, as was shown in this paper, there were also many other saddle points that start to dominate the spectral form factor. And because here the BPS index is protected under supersymmetry, you can compare this result to the strong coupling limit. And they found that each saddle points in the spectral form factor can actually be identified with a particular complex black hole solutions. That was also discussed by some other authors in the literature. And these complex black hole solutions, they involve orbifold black holes as well as black holes that have shifted chemical potentials. Okay? So this is a case where in the BPS context, you actually see that there are actually, after the initial decay given by the black hole in the Lorentzian signature, you actually have a family of other complex solutions that saved you from the discreteness problem. Okay, so of course, the BPS states still involve quantized charges that are spaced evenly, and they certainly doesn't contain the random matrix statistics. We don't really expect the story to be the same for non-supersymmetric black holes, which we believe that should have chaotic features. So how do we actually put in chaos in the story? So we want to find some way to look for chaos, building on this result of the free theory. So there are actually two ways that you can think of to add in the chaos. So first, as a toy example, we could stay in the free theory, while we can play a game and take the single particle spectrum to be chaotic, say from a random matrix, okay? So that's like a toy example that you can do. Of course, the second way or the ultimate way is to turn on the Hooft coupling. So here I will first briefly discuss the first way, which is a toy example. The main purpose of that is not saying that that is correct ansatz for the black hole at late time, but to highlight the difference between the first way and the second way. And I will argue that the second way is very, very different from the first way, okay? So now, if we take the single particle spectrum to be chaotic, basically what happens is that these little z functions in the matrix integral, because they come from the single particle partition function, essentially these little z functions, they are partition function of a member, specific member in the random matrix theory. Now, what changes is that, for example, in the first case that I discussed, if I put the theory on S3, these solutions to the equations Zn equals to 1 have a very regular structure, and it is periodic along the imaginary direction. On the other hand, if you put the single particle partition function to be from a random matrix theory, these solutions will start to look very random in the complex plane. So in fact, in this picture, I only took 2 harmonic oscillators with energies that are incommensurate. But if you really take a random matrix theory, you expect these solutions to be much more chaotic, located on the complex plane. Now, the result of this is that this will result in a huge irregular fluctuation in the spectral form factor. Because as I said, each of these solutions actually correspond to a saddle point that might contribute in the spectral form factor. And if these solutions appear in a chaotic way, this means that they are chaotic and very, very large, namely exponentially large, e to the order n squared large fluctuations in the spectral form factor of the full theory. In other words, large but order 1 fluctuations in the single particle spectral form factor gets enhanced to e to the order n squared large fluctuations. So it is a kind of chaos from order, because the underlying theory is not really an interacting theory, but here you get a huge fluctuation in the spectral form factor. Now, this is of course very, very different from the true random many-body chaos that we expect. And to get the true many-body chaos, we will really have to turn on the Hooft coupling, and there's no other way that I know of. Now, perturbatively speaking, if you just turn on a small Hooft coupling, you don't expect the saddle points that we found to disappear at short time. you expect a weak tooth coupling to just deform the saddle points in the free theory slightly at short time. The reason is that physically, as I said earlier, these other saddle points, they correspond to very, very long wavelength fluctuations in the density of state. And if you just have a little bit of tooth coupling, the originally degenerate states at each integer value would just split a little bit around each of the integers. And you still have these long wavelength fluctuations in the density of state. So that's the reason that you still expect these other saddle points at short time. However, when we expect this picture to break down at a very long time, a long enough time, physically speaking, what you expect is that even with a very, very weak coupling, you expect the spectrum to develop some random matrix statistics at a very fine scale. Namely, if we zoom in to this very detailed scale, we should start to see some random matrix statistics. And we expect the ramp should emerge at a later time. Okay. So in the last part of my talk, I will try to argue that this conjectural ramp, or this would-be ramp, should behave very differently from all of these short time saddles. So all the short time saddles that I mentioned earlier, they are in the deconfined phase. In other words, the Polyakov loops have classical expectation values in all of these saddles. I will try to present some arguments that the ramp is very different in the sense that it behaves as if it is in a confined phase. In other words, the Polyakov loop do not acquire classical expectation values during the ramp. Because of the limitation of time, I will just sketch the general idea, and you could ask me about the detail later. Now, one of the concrete questions we can ask here is, what is the expectation value of the Polyakov loop as a ramp? In other words, we are considering some beta plus IT where T is fairly large and wrap a thermal Wilson loop around the circle. Or more generally, we can also consider a microcanonical example version of the calculation. Of course, since we are not able to really do the computation exactly here, the following statement will be based on some qualitative physical arguments. So let me start by seeing what the bulk picture is trying to tell us about. Now, ideally, similar to what was done in Edwards' paper in '98, we will also have a one boundary description of what happens during the ramp. And then we can simply use the string wall sheet picture to answer this question. We can ask whether the time circle in that one boundary geometry shrinks to a point or not. And that would tell us whether the Polyakov loop has a classical VEF or not. But we don't really have this choice, as we know this is a huge open question in this direction. On the other hand, as was proposed by Sashankar and Stanford, we would assume that under some suitable time average, the late time ramp at strong coupling in the microcanonical example is given in the bulk by a saddle point, which is the so-called double cone wormhole. So here I'm drawing it as in this picture as a double cone. So now the idea is that if we just wrap the Polyakov loop on one side, in other words, we wrap a Wilson loop on the right side, the string has nowhere to end in the bulk because the topology of the bulk geometry is a cylinder, it's a wormhole. So at the classical level, the answer should be 0. So here I'm deliberately not writing down the precise formula. I'm basically just write the word Polyakov loop because the precise statement has to be formulated by using the adjoint line because of the center symmetry in the gauge theory. But I haven't really told you about that. So here the idea is just because it's a wormhole, then the expectation value of the Polyakov loop under the time average should be 0. Naively, you could say that we could still have a non-zero and actually large order 1 value of the Polyakov loop at any moment of time. But it could well be that when we get 0 here, it simply says that this order 1 and large fluctuation averages to 0 over time, okay? But we can actually rule this out by looking at the time average of the square of the Polyakov loop. In other words, we consider the Polyakov loop square and then take the time average. Now, the interesting phenomenon here is that once you consider this quantity, there is a classical diagram in the bulk. In other words, you wrap a Wilson loop on the right and another Wilson loop on the left, and there can be a classical string worldsheet that connects these two Wilson loops by going through the wormhole. So there can be a string worldsheet that stretches across the wormhole. And in the bulk, it corresponds to a cylinder diagram in string theory. So you know that it should not give you any large n factor. Here I wrote it as order 1 over n squared, where the 1 over n squared simply comes from the normalization of the Polyakov loop. And this will tell you that not only the average of the Polyakov loop is 0, its fluctuation in time is also very, very small. Okay? So as a conclusion here, these are saying that the Polyakov loop has only a very, very tiny wave, somewhat similar to the ordinary confined phase. However, here the physics is of course quite different from the usual confinement. We still have exponentially many high-energy states involved in the calculation. The physics behind is not because we don't have enough states, but because of huge cancellation among the high-energy states. And we should really avoid calling this, this phase as a confined phase here. Also, another implication of this is that if there already exists certain one-boundary classical geometries, or the so-called half wormhole that are envisioned in the literature that describes the ramp, this is an argument that's saying that the time circle of the half wormholes should not be contractible in the bulk. Of course, this is a feature that you might have just guessed naively. For example, this will be consistent with the proposals in the literature, such as the eigenbrains picture. But it could, of course, also well be that the late time behavior of the ramp is not given by any kind of classical geometry. Now, for the last few minutes, let me just briefly mention that in the last few slides, I gave you a bulk picture of what the Polyakov loop should be. But there is also a nice way to think about the Polyakov loop from the boundary theory point of view. And you can compare these two pictures. Now, the trick here is to think of SUN not as a gauge symmetry, but as a global symmetry of the theory before you integrate over the zero mode of the gauge field or the holonomy. Okay, so before you integrate over the zero mode, the theory has a SUN as a global symmetry. And the Polyakov loop in some particular representation R in the SUN is closely related to the partition function of all the states in some representation R in this ungauged model. So here in terms of equation, I'm writing it as the Polyakov loop in some representation R, or in other words, the character in some representation R will be proportional to the spectral form factor or the analytically continued partition function in that representation. The point of rewriting the Polyakov loop in this way is that random matrix theories with global symmetries have been studied in the literature. For example, in this paper by Dan Kapek, Raghu Mahajan, and Dr. Stanford, as well as in this paper by Luca. So if we just assume that the ungauged model, in other words, the N-4 super-Yang-Mills model before you integrate over the zero mode of the gauge field, this model has strong coupling and late time. If we assume that it is described by this random matrix universality, you can then use their results to make a lot of predictions on how the Polyakov loop should behave. And even though I don't have time to go into the detail here, you'll find that such predictions, at least at the level of large N scaling, you agree with the wormhole pictures mentioned previously. So now let me try to summarize. So in this talk, I discussed the spectral form factor in large N gauge theories. And one particular way that you can use to summarize the result is to organize everything in an unconventional phase diagram. So here I'm drawing a two-dimensional phase diagram where the horizontal axis is fairly unconventional. It's the time argument in the spectral form factor, okay? And the vertical axis is the Hooft coupling. Now, as we solved explicitly in the free theory, the horizontal axis at lambda equals to 0 is divided into many, many small pieces. In the free theory, we ran into the crisis regarding the discreteness of the spectrum, and we found that there are a family of other saddle points that start to come in and save the day. And there are actually different phases in the sense that they preserve different, they are distinguished by these order parameters, or they preserve different symmetry, different subgroups of the center symmetry. Now with a little bit of coupling, with weak coupling, we expect these saddle points to persist at short time. In other words, these lines will extend into this two-dimensional plane. They will be deformed slightly in some particular way. While at very long time, we will expect that the RAM to emerge. So there should be a phase boundary that starts to come in at infinity once you go to finite to Hooft coupling. And another point that we argued in this talk is that the RAM already has a very, very different nature from all the early time saddle points. And we argue that it can be diagnosed, for example, by looking at the expectation value of the Polyakov loop. So the RAM also is separated from all these early time parts by a phase boundary, which I'm drawing in red here. Now, as you go to strong coupling, in the strong coupling limit, in other words, the coupling is very, very large. To my knowledge, we only know two phases. We only know the black hole phase and the ramp, okay? And as I argued, they should be separated by a phase boundary here. Now, an interesting question is, of course, if you look at this phase diagram, you see that it's unclear where all these phases at weak coupling goes in the strong coupling. So there are two possibilities. One possibility is that they become some other saddle points that we are not aware of as strong coupling. Or the other possibility is that there are some phase transition that happens at finite to Hooft coupling that annihilates all these different phases. And there must be phase transition. As I said, they are separated by different order parameters under the ZN global center symmetry. So that's basically all I want to say. Thank you very much.
All right, any questions?
Yes.
Good one.
Have that some of the lines in the bottom are black holes where you by a CN symmetry.
Yeah, so that's a possibility that they still remain in the strong coupling limit. But as you see here, for example, you could have a C2 quotient saddle point, but it appears, for example, many, many times in the free limit. But there must be some mechanism that they become merged into one single saddle point as strong coupling. I actually think that that's probably what happens. For example, even if we forget about all these other saddle points, we still have the periodically recurrence of the early saddle points. And we know that as strong coupling, all these periodically recurrence should also be merged to a single saddle point, which is the black hole. So that I think is the, well, that could be what's really happening. Okay. Yeah.
Can you click on the chat window?
Yes.
Just click on the chat.
Yeah, I can.
The question was how important was it that you had a large Ngauge theory?
Yeah.
So for N free boson.
Yeah, the question, how is important
Yes,
is the gauge
yes.
theory versus free boson?
So I would say that so here, so Alex is asking how important that we already have a large Ngauge theory, and he's claiming that if we have N free bosons, the spectral form factor will decay to exponentially small values at order 1 time. I believe here when you say that the N free boson, you are saying that N free bosons with the same mass, and I agree that in that case it probably decays to order 1 time because before it starts to bounce back again. So I would say that in that case, the spectrum is even more special than the large Ngauge theory, because in the large Ngauge theory, there is the gauge constraint. So the gauge constraint actually makes the spectrum somewhat more generic than the spectrum that you will have for just n free scalars. So in the large N gauge theory, what we found is that the spectral form factor does not really decay to exponentially small. Well, I'm not sure whether that already answers the question. Yeah, okay, thanks.
Anyone else? All right, let's thank Yiming again.